Let's say we want to treat gas that contains ammonia. And the amount of gas to be treated is 25,000 feet cubed per hour. The concentration of ammonia in this gas is 2% by volume. And since we know that water is a good solvent of ammonia, we choose to use water as the solvent in this problem. And we assume that this water has no ammonia in it. The temperature of the entering gas and absorbent is at 68 degrees Fahrenheit. So that means the temperature of the column is 68 degrees Fahrenheit and pressure is at 1 atm. Also given the ratio of liquid flow to gas flow, or the L/G ratio, which is 1.25 pounds of solvent over 1 pound of gas to be treated. Now the question, if the design pressure is 0.5 inch of water with every feet of packing, what should the mass velocity of gas be? So what is an adequate GY, and what would the diameter of this tower be? Finally, what is the ratio of the gas velocity over flooding velocity? U0 over flooding velocity. Now we can use a generalized correlation and also specific data for interlock saddles for this absorption column. So here we are going, for this problem, we are going to use interlock saddles as the packing inside this absorption column. To solve this problem, first we need to calculate the density of gas and water. The gas to be treated has 2% by volume of ammonia in it, so we have to first determine the molecular weight of this mixture of gas. So the molecular weight of the gas, the average molecular weight of the gas is 29. 29 is the molecular weight of air, multiply 0.98, which is the concentration by volume of air in the mixture, and we add this with 17, which is the molecular weight of ammonia, multiplied by 2% by volume given in the problem. And this would give us an average molecular weight of the gas mixture of 28.76 pounds per pound mole of gas mixture. Next, we need to calculate the density of this gas mixture. To do this, we'll use the ideal gas law equation, which is PV equals to nRT, where P is pressure, V is volume, N is number of moles, R is the universal gas constant, and T is temperature. Rearranging this equation, we get M over V, M for mass, over volume equals to the average molecular weight of the gas times P divided by R and T. So M over V is the density of gas, or rho y, and that is equals to the molecular weight of gas, which we calculated just now, 28.76, multiply with 1 atm, which is the pressure inside the absorption column, divide by the universal gas constant, 0.73024, and multiply this with temperature, 460 plus 68. This is a 460 is a constant to convert Fahrenheit to Rankine, since the universal gas constant that we use here has Rankine in its units, and this would give us a density of gas of 0.070 mistake 0.07459 pound per feet cube. Then we also need to know what is the density of the solvent. Since it's water, we can look it up in a reference table or from the internet. It is 62.3 pounds per feet cube. Now we have rho y and we also have rho x, so that we can use these values in the figures that I talked about in the previous videos. Now we are going to calculate gy, and to do that we need to use this figure. Looking at the x-axis, we can obtain a value for this parameter using the values calculated before. So it equals to L over G, which is given, multiplied by rho x over rho y square root, and this gives us a value of 1.25 multiplied with 0.07459 divided by 62.3 to the power of 0.5 or square root, and this calculates to 0.0433. Looking at this figure and at a design pressure of 0.5, we can obtain the CSFP value. For 0.0433, that is at about here, we go up this line up to 0.5 design pressure and move to the left to get a rough value of 1.38. This means the y-axis parameter of CS Fp to the power of 0.5 and V to the power of 0.05 is equals to 1.38. For interlock saddles, Fp is given as 92, and at 68 degrees Fahrenheit, the kinematic viscosity of water is 1.0 centistokes. So Cs is equals to 1.38 divided by 92 to the power of 0.5 times 1 to the power of 0.05, which gives us 0.144. Now we need to determine what is Gy. From previous videos, I state that U0, or the gas velocity, is equals to Cs, which we got from the previous figure, multiply with the density of the solvent minus the density of the gas, divide by the density of the gas to the power of 0.5. And if we just plug in the values, (62.3) minus 0.07459 divide by 0.07459 to the power of 0.5, it would give us the gas velocity of 4.16 feet per second. Now we need to convert this to mass gas velocity instead of gas velocity. And we know that Gy is equals to U0 multiplied by the density of the gas, and that equates to 4.16 times 0.07459, which is the density of the gas. And we also need to change from seconds to hours so that it is consistent with the amount of gas that is processed given in the problem. So we multiply with the conversion factor of 3,600 seconds every hour, and this gives us a mass gas velocity of 1,117 pounds of gas every feet cube every hour. To calculate Gx, or the solvent rate, is simple because we know the ratio, L over G ratio, which is, and to calculate Gx, or L, it's just a matter of 1.25 multiply with Gy, which is 1,396 pounds every feet cube every hour. Now we need to come up with the actual air mass velocity given the design requirements. So calculated before, Gx is equals to 1,396. This is a list of Gx values from dry to very large solvent flow rate. Gx of about 1,300 is somewhere between this line and this line. So if we were to estimate it to be somewhere in between, like this, then we'll be able to determine the actual Gy value. Now we know that the design pressure is 0.5 as stated by the problem, that is around here. We go from here to this estimated line, and from here we move down to obtain our Gy value. Now that gives us a Gy value of 1,000 pounds per feet square per hour. This unit here is in feet square instead of feet cube because this diagram is for every feet of packing. Now given that the design mass gas velocity is 1,000, so Gy is 1,000 pound per feet square per hour. This is for every feet of packing. We can calculate the total gas mass flow rate, which is total gas equals to 25,000 feet cube per hour multiply with the density of the gas mixture, 0.07459 pound per feet cube, to obtain the amount of gas every hour, which is 1,865 pounds per hour. Knowing this, we'll be able to calculate the cross-sectional area of the column. So the area of the column is equals to 1,865 pounds per hour divided by the amount of gas rate to be treated. And this would give us 1.865 feet square. If the area of the column is to be so, this area is 1.865 feet square. And we back we use this number to calculate the diameter of the column. So D is equals to 4 times the area, 1.865, divide by pi, and we square root this to get the value of 1.54 feet. Now the last part of the question is to calculate the gas velocity to flooding ratio so that we would have an idea of how fast can we allow the gas to flow through the absorption column before it floods the column. We need to refer to this figure again to obtain this ratio. Using the flooding pressure drop of delta P equals to 2.0 inch of water for every feet of packing. So in this figure, it only shows the delta P, a maximum value of delta P of equals to 1.5. So we can estimate a line above this to come up with our design value for delta P equals to 2.0, or when the absorption column will be flooded. So since this is 1.5, so if we just estimate it to be a straight line that goes something like that, using the same gx/gy parameter value as calculated before at 0.04, and we move up to, here's one design value, this was the first design value, and to also the flooding design value of about here. So from the values obtained just now, we got it at 1.38, but for this it's somewhere close to 2. Let's just use this value, 1.95. So that is the design value at delta P equals to 2.0. So to calculate the gas velocity to flooding ratio, we just divide this value, these two values. So the gas velocity U0 over the flooding velocity ratio would be 1.38 divided by 1.95, which is equals to 0.71. It can be simplified like this because gas velocity U0 and also the densities, and the densities are also constant. So in the end, if we divide these two values, you would get the gas velocity ratio. But this is the gas velocity ratio for the design condition, the condition that we want to maintain the tower at, while this is at a condition when it could flood, so that we get an idea of how much of the velocity that we are using is a part of the flooding velocity. So in this case, it's about 71% of the flooding velocity. So to sum up the values that we've calculated for this problem, we found that the gas velocity is 1,396 pounds per feet cube per hour. The diameter of the column is 1.54 feet, and the gas velocity flooding velocity ratio is 0.71. And this sums up the solutions of this problem, and I will see you in the next video.